there is a small arrival taking place above you. From somewhere beyond the air, a packet of light reaches the upper atmosphere, passes through shifting layers of nitrogen and oxygen, and continues toward the surface of Earth. It may end its journey on a telescope mirror. It may be absorbed by a camera sensor, or it may enter a human eye, where its energy becomes a signal carried inward by the nervous system. For the briefest moment, something that began far away becomes part of your present. We often speak of a photon as though it were a tiny traveler launched from the heart of a star and moving cleanly through space until it reaches us. That image is useful, but the real story is more intricate. Deep inside a star, light does not move outward in a straight line. The stellar interior is too dense. Energy is absorbed, released, scattered, and absorbed again, passing through matter in countless exchanges. So the light arriving tonight is not usually a single untouched messenger that escaped directly from a stellar core. It is better understood as the final expression of a much older flow of energy. That flow begins where pressure and temperature are high enough for atomic nuclei to fuse. Inside a star like the Sun, hydrogen nuclei move through a crowded plasma. Under immense pressure, some of them join through a sequence of reactions that gradually builds helium. A small amount of mass is converted into energy. Part of that energy appears as high-energy radiation, while another part is carried by particles moving through the stellar interior. Nothing about this beginning resembles visible starlight. The first radiation associated with fusion is far more energetic than the light your eyes can detect. But the star does not allow that energy to leave quickly. It enters a region where charged particles and free electrons fill nearly every path. A photon may travel only a short distance before interacting with matter. Its energy is taken up, redistributed, and released again in a new form and direction. There is no open corridor leading outward. Instead, energy works its way through the star by a long sequence of exchanges. In the radiative zone of the Sun, this process can take an immense span of time. Exact estimates depend on how the transport is modeled. But the important point is simple. The energy that becomes sunlight may spend many thousands of years moving outward before reaching the layers where matter is thin enough for light to escape freely. By then, the original high-energy radiation has been transformed. Repeated interactions have spread its energy across many lower-energy photons. Near the surface, convection also plays a role, carrying hot material upward and cooler material downward, until energy reaches the photosphere, the visible layer we loosely call the surface of the Sun. From there, light finally enters open space. The star releases it in every direction. Most of those photons will never meet a planet, a telescope, or an eye. They will continue outward through the widening dark, carrying energy away from the star. Its pace changes completely. Inside the star, progress was indirect, interrupted, and shared through matter. Beyond the photosphere, a photon can move at the speed of light through the vacuum, covering the distance from the Sun to Earth in a little over 8 minutes. The long delay is over, the open journey has begun. And this is the first quiet truth carried by starlight. What arrives quickly across space may have taken an age to reach the place from which it could leave. Beyond the visible surface of a star, the crowded interior gives way to a different kind of passage. The light is no longer trapped inside dense plasma, but it is not yet moving through empty interstellar space. It must first cross the star's outer atmosphere, where temperature, density, and magnetic fields shape what escapes. In the Sun, the photosphere is only the layer from which visible light reaches us. Above it lies the chromosphere, followed by the corona, a thin outer region extending millions of miles into space. Matter there is sparse compared with the layers below, yet it is active. Charged particles move along magnetic fields. Loops of hot plasma rise above the surface. Small changes in density can scatter or absorb certain wavelengths while allowing others to continue outward. Most visible photons pass through these upper layers without being stopped. Some interact once more before leaving, others escape almost immediately. Each carries an amount of energy connected to its frequency, and together they form the broad range of radiation produced by the star. Visible light is only a narrow part of that range. The sun also releases infrared radiation, which we often experience as warmth, and ultraviolet radiation, which carries more energy than visible light. It produces radio waves, X-rays, and smaller amounts of radiation at still higher energies. The balance changes depending on which layer of the sun is being observed and what is happening there. A telescope designed for visible light reveals the bright photosphere. An ultraviolet telescope can show activity higher in the solar atmosphere. X-ray instruments reveal extremely hot plasma shaped by magnetic fields. The same star can appear almost unrecognizable when seen through different portions of its spectrum. The photon traveling outward belongs to one of these regions of energy. Its color, if it falls within the range human eyes can detect, is not something painted onto it. Color is the experience produced when light of certain wavelengths reaches a visual system. Red light has a longer wavelength and lower frequency than blue light. Blue light carries more energy per photon. Between them lies the familiar band of colors that can be spread apart by a prism or gathered together into what appears as white sunlight. The star does not send those colors in separate beams. They leave together, overlapping across space. Only when matter separates them, or an instrument records them with precision, does their structure become obvious. A raindrop can divide sunlight into a rainbow. A glass prism can do the same. A spectrograph inside an observatory performs a more careful of this separation, spreading light across a detector so that small differences in wavelength can be measured. Those differences carry information. Atoms and molecules interact with light in particular ways. Each kind of atom can absorb or emit certain wavelengths determined by its internal energy structure. When light passes through cooler gas in the outer layers of a star, specific wavelengths may be absorbed. The resulting spectrum contains dark lines where some of the light is missing. These lines are not flaws in the starlight, they are records of matter. Hydrogen leaves one pattern, sodium leaves another. Calcium, iron, magnesium, and many other elements leave their own recognizable marks. By studying the arrangement and strength of these lines, astronomers can identify what a star contains without touching it or sending an instrument anywhere near its surface. The photon that survives this process may carry a wavelength that passed through freely. Another photon nearby may be absorbed by an atom, raising one of its electrons to a higher energy state. The atom can later release energy again, often in a different direction. From far away, the combined result becomes a spectrum filled with structure. This is one reason light is more than illumination. It is evidence shaped by every environment it has crossed. Once beyond the corona, sunlight enters the solar wind, a thin flow of charged particles expanding outward from the sun. The space between the planets is not completely empty. It contains electrons, protons, magnetic fields, dust grains, and atoms so widely separated that they would seem almost absent by ordinary standards. A visible photon can pass through most of this region without interacting at all. Its path from the sun to Earth is nearly straight, though gravity gives every path through space-time its shape. The sun's own gravity affects the geometry around it, but for light already moving outward toward Earth, the result is far too small to notice in an ordinary description of the journey. The distance is about 93 million miles. At the speed of light, the crossing takes roughly 8 minutes and 20 seconds. During that time, Earth continues along its orbit. The sun turns. plasma shifts across the solar surface. Magnetic fields move and twist, yet the light keeps the direction it had when it left. What arrives at Earth is therefore not an image of the Sun, as it is at that exact instant. It is an image of the Sun a little more than 8 minutes earlier. This delay is small enough to fit inside a morning routine, but it introduces a principle that applies everywhere in astronomy. To look outward is to look backward. Distance becomes time because light does not travel infinitely fast. The moon appears a little more than 1 second in the past. The outer planets appear tens of minutes or several hours in the past, depending on their positions. Nearby stars are seen years ago. Distant galaxies are seen millions or billions of years before the present. Even the sunlight falling across a room is a record. It began its open space journey before it reached the window, before it crossed the atmosphere, before it touched the floor or the edge of a resting hand. The delay is too brief for human awareness to notice, but the light still belongs to an earlier moment. There is another way to describe what moves across that distance. In classical physics, light behaves as a wave. It has wavelength and frequency. It can interfere with itself, bend around edges, and form patterns of brightness and darkness. In quantum physics, that light arrives in discrete amounts of energy, called photons. A detector does not receive an infinitely divisible washi. It records individual interactions. Both descriptions are necessary. Light is not sometimes a wave and sometimes a particle in the ordinary sense of changing from one familiar object into another. It follows quantum rules that do not fit completely into either everyday category. The words wave and particle are models, each revealing part of what experiments show. For the journey we are following, the photon gives the story a useful scale. One release of energy, one path through space, one final interaction. But around it are countless others, streaming outward from the star in every direction. The sun emits so many photons that daylight feels continuous. Their individual arrivals blend into brightness, warmth, shadow, reflection and color. Only a tiny fraction will meet Earth. A smaller fraction will enter the atmosphere above the night side or pass through a telescope pointed toward the sun from space. Fewer still will strike a particular detector or reach a particular eye. Yet no photon chooses its destination. There is no search, no aim, and no awareness inside the journey. There is only the unfolding of physical law across distance. The light leaves the star carrying energy and information. Ahead lies a planet wrapped in air, where the next part of the journey will depend on clouds, molecules, dust, angle, and color. At the edge of Earth, there is no sharp border where space ends and air begins. The atmosphere thins gradually, molecule by molecule, until the distances between particles become immense. A photon arriving from the sun or a star does not cross a visible boundary. It simply begins to encounter matter more often than it did before. For visible light, the first encounters are usually rare. The upper atmosphere is thin, and many photons pass through it without interruption. But the deeper the light travels, the more crowded the air becomes. Nitrogen and oxygen dominate. Water vapor, carbon dioxide, ozone, dust, salts, smoke, and tiny droplets add their own influence. From this point onward, the journey depends on wavelength. A blue photon and a red photon may enter the same patch of sky along nearly parallel paths, yet the atmosphere does not treat them in quite the same way. Molecules much smaller than the wavelength of visible light scatter shorter wavelengths more strongly than longer ones. Blue light is therefore redirected more readily than red light. This scattering does not destroy the photon. It changes the direction in which it travels. A photon that had been moving toward the ground may be sent sideways. Another may be redirected upward. Some are scattered more than once before they are absorbed or finally emerge from the atmosphere. Across the entire sunlit sky, Countless such changes create the familiar field of blue overhead. The sky is not blue because the air itself carries a blue color. It appears blue because sunlight has been separated by the atmosphere, with shorter, visible wavelengths sent across the sky more efficiently. Violet light is scattered even more strongly, but the sun emits less of it. Part of it is absorbed high in the atmosphere, and human vision is less sensitive to violet. The combined result is the blue that the eye recognizes so easily. A photon arriving from a distant star at night enters the same atmosphere, but the surroundings are different. There is no nearby flood of scattered sunlight to brighten the whole sky. The star remains a point against a darker background, and its light can be followed with far greater contrast. Even then, the air does not leave the image untouched. The atmosphere is always moving. Warm air rises, cooler air sinks. Winds slide across layers of different temperature and density. Each region bends light by a slightly different amount. As starlight passes through these changing pockets, its apparent direction shifts from moment to moment. To an eye on the ground, the star seems to tremble. Its brightness may flicker, its position may wander by an amount too small to notice directly, but large enough to blur a telescope image. Sometimes the changing refraction briefly separates colors, producing tiny flashes of red, green, or blue. This is the origin of stellar twinkling. The star itself may be radiating steadily. The movement is introduced much closer to home in the final miles of the photon's path. A calm point of light at interstellar distance becomes restless only after entering the air above the observer. Planets usually twinkle less. They appear point-like to the unaided eye, but through the atmosphere they occupy a small disk rather than a single, unresolved direction. Light from different parts of that disk passes through slightly different air. The fluctuations tend to average together, giving the planet a steadier appearance. Near the horizon, the effect grows stronger. Photon from a low star must travel through more atmosphere than one arriving from overhead. Its path cuts across a long slant of air, eating more molecules, more dust, and more layers of changing temperature. The image becomes less stable. The star may look dimmer, redder, and more active than it does when higher in the sky. The same long path shapes sunrise and sunset. When the sun is near the horizon, its light passes through a much greater thickness of atmosphere before reaching the ground. Much of the blue light is scattered away from the direct line of sight. The light that remains is weighted more toward red, orange, and gold. The photons have not slowed into new colors. Many of the shorter wavelength photons have simply been redirected elsewhere, leaving a different balance in the beam that reaches the eye. Dust, haze, smoke, and droplets can deepen or soften these colors. Larger particles scatter light differently from individual molecules, sometimes washing the sky in pale tones, and sometimes building layers of copper and crimson along the horizon. Every sunset is therefore a record of both sunlight and the state of the air through which it has traveled. Other wavelengths meet more decisive barriers. Ozone in the stratosphere absorbs much of the sun's most harmful ultraviolet radiation. Water vapor and carbon dioxide absorb broad regions of infrared light. High-energy X-rays and most gamma rays are stopped in the upper atmosphere. Many radio wavelengths pass through, while others interact strongly with charged layers of the ionosphere. Earth's atmosphere is therefore not a transparent shell. It is a filter with windows. Visible light passes through one of the widest windows, which is one reason human eyes evolved to use it. Certain radio waves also reach the ground well enough for large dishes to study the sky. Much of the rest of the electromagnetic spectrum must be observed from mountaintops, high-altitude aircraft, balloons, or spacecraft above the atmosphere. An X-ray photon from a distant black hole may cross thousands of light years of space and then be absorbed before reaching the surface. To detect it, an observatory must wait above most of the air. An infrared photon may be swallowed by water vapor, unless the telescope stands in a dry region or operates in space. The final obstacle can be the last thin layer surrounding the planet. For ground-based astronomers, the atmosphere is both shelter and limitation. It protects life from radiation that would damage cells. It moderates temperature and carries the gases on which living systems depend. Yet it also blurs images, blocks wavelengths, and adds its own glow to the night sky. Observatories are often built on high, dry mountains because there is less air above them and less water vapor to absorb incoming light. The atmosphere there is not absent, but the path through it is shorter and often more stable. Modern telescopes can also use adaptive optics, reshaping a mirror many times each second to compensate for atmospheric distortion. The correction begins by measuring how a reference star appears to change. A computer calculates the shifting pattern, and small actuators alter the mirror's surface in response. Light that arrived as a blurred wavefront can be brought closer to the image it would have formed above the atmosphere. The telescope is, in a sense, learning the air moment by moment. Long before such instruments existed, people learned the atmosphere in other ways. A star's color near the horizon, the clarity of a familiar constellation, or the steadiness of a planet could reveal something about weather and visibility. The sky was not only a map beyond Earth, it was also a reading of the air immediately overhead. That connection remains. From a resting place beneath a roof or beside a window, the atmosphere may seem like empty distance. Yet, every breath belongs to the same layered structure that bends starlight, scatters the blue of day, and turns the setting sun toward red. The air close to the skin and the air high above a telescope are part of one continuous envelope. For the photon, this envelope may be the final complicated region of a journey that began inside a star. Some photons will be absorbed by a molecule and converted into molecular motion. Their energy becomes part of the atmosphere's warmth. Some will scatter upward and return to space. Some will strike a cloud droplet, reflect between water and air, and emerge in a new direction. Under the right geometry, sunlight entering raindrops can be refracted, reflected, and separated into a bow of color. Others pass almost directly through. A photon from the sun may reach the ground and be absorbed by soil, water, leaf, stone, or skin. A photon from a star may enter a telescope and end as an electrical signal. Another may fall into the pupil of an eye. Before that final interaction, there is one more narrowing of the journey. The light that once expanded outward in every direction from a star now approaches a small opening only a few millimeters wide. Beyond it waits a transparent lens, a curved surface, and a living layer of cells prepared to turn arriving light into sight. Once light has crossed the boundary of a planetary atmosphere, the scale of its journey begins to change. The distances between planets are large enough to measure in minutes or hours of light travel. Between stars, the same speed must work across years. A photon leaving the sun needs a little more than 4 years to reach the nearest star system. To cross the Milky Way, it may travel for tens of thousands of years. Space across those distances is not completely empty. The region between stars contains gas, dust, magnetic fields, energetic particles, and the remnants of earlier generations of stars. The material is thin by any earthly standard. A laboratory chamber would seem crowded by comparison. Yet, over a path measured in light years, even sparse matter can alter what reaches an observer. Hydrogen is the most common element in this interstellar medium. Some of it exists as separate atoms. Some is ionized, with electrons no longer bound to nuclei. In colder regions, hydrogen atoms can pair into molecules, gathering with other material inside clouds, where new stars may eventually form. Mixed through this gas are grains of dust. The word dust can make them sound familiar, But interstellar grains are not simply the same material that settles on a shelf. They may contain silicates, carbon-rich compounds, water ice, and other frozen substances. Many are smaller than the width of a human hair, though their sizes and structures vary. A photon passing through a clear region of interstellar space may travel for a very long time without meeting one. Inside a denser cloud, the odds change. Dust grains absorb and scatter light. Shorter visible wavelengths are usually affected more strongly than longer ones, which can make distant stars appear redder than they truly are. This process is called interstellar reddening. It resembles the reddening of the sun near the horizon, but the material responsible is different. In the atmosphere, molecules and particles scatter light during the last part of the path. Between stars, dust may shape the spectrum across years or centuries of travel. The color that reaches Earth is therefore not always the color that left the source. Astronomers must estimate how much light has been removed and how strongly the spectrum has been changed. They compare stars of known type, measure the behavior of different wavelengths, and use models of dust along the line of sight. Without that correction, a star can seem cooler, dimmer, or farther away than it is. Dust also creates dark shapes across bright backgrounds. A cloud placed in front of a dense field of stars may block visible light so completely that it appears as a hole in the sky. The region is not empty. It is filled with material. In infrared light, the same cloud can become partly transparent. Longer wavelengths pass through dust more easily, allowing instruments to see stars hidden inside. The cloud may also emit infrared radiation of its own after dust grains absorb starlight and warm slightly. Light can therefore reveal the obstruction and the hidden interior, depending on which photons are received. There is no single transparent universe. Every wavelength has its own landscape of open paths and closed ones. Visible photons may be stopped by a molecular cloud. Radio waves can cross regions that visible light cannot. X-rays may pass through some material while being absorbed by thicker columns of gas. Gamma rays travel far, but they too can interact with radiation and matter under the right conditions. The interstellar medium is not only a filter, it can also be a source. Gas emits light when atoms or molecules change energy states. In regions where young, hot stars produce strong ultraviolet radiation, nearby hydrogen can be ionized. When electrons later recombine with protons, the gas releases photons at characteristic wavelengths. Large clouds begin to glow. Some of the red light seen in emission nebulae comes from hydrogen undergoing these transitions. Other atoms add their own lines, creating spectra that reveal temperature, density, motion, and composition. Elsewhere, cooler clouds emit radio waves from molecules rotating or vibrating. These signals allow astronomers to identify substances in space that cannot be collected directly. Carbon monoxide is often used to trace molecular hydrogen, which is harder to detect under the same conditions. The photon journey becomes part of a larger exchange. Starlight enters the cloud. Matter absorbs part of it. Atoms, molecules, and grains release energy again. New photons leave with different wavelengths and directions. A cloud may hide one kind of light while creating another. Some photons are scattered without losing much energy. When light from a bright star reflects from nearby dust, the region can form a reflection nebula. Because shorter wavelengths scatter efficiently, these nebulae often appear blue. The dust does not shine by fusion. It borrows the light of a nearby star and sends part of it elsewhere. A photon that eventually reaches Earth from such a nebula may have taken an indirect route. It left the star in one direction, struck a dust grain, and was redirected toward the observer. The path contains a bend, and that bend can reveal the shape and location of material that would otherwise remain unseen. Scattered light can also become polarized. Polarization describes the orientation of light's electric field. Ordinary starlight often contains many orientations mixed together. Reflection, scattering, and passage through aligned dust grains can favor some orientations over others. By measuring polarization, astronomers can study structures that a simple image does not show. Dust grains in space may align with magnetic fields. The light passing through or scattering from them carries a trace of that alignment. A photon can therefore arrive with information about a magnetic field it never touched in the way a solid object touches another. Its interaction with matter along the path has shaped the pattern that a detector can measure. The interstellar medium is also moving. Clouds rotate, expand, collapse, and collide. Gas flows outward from stars. Shock waves from supernovae push through surrounding material. The motion changes the wavelengths of emitted and absorbed light through the Doppler effect. When a source moves toward an observer, its spectral lines shift toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. The change may be too small for an eye to notice, but a spectrograph can measure it. From those shifts, astronomers reconstruct motion along the line of sight. A glowing cloud may look still in a photograph, yet its spectrum can reveal gas moving in opposite directions, shells expanding, or material falling inward. Light adds a hidden dimension to the image. The photon itself is not carrying a written record of speed. Its frequency is the record. The same principle allows the motions of stars to be measured. It helps reveal binary systems, stellar winds, rotating galaxies, and planets pulling on their host stars. Across the universe, movement becomes readable because light changes in consistent ways. Interstellar travel also changes the apparent brightness of sources. Light spreads as it moves outward. The same amount of energy occupies a growing area, so a distant source looks fainter than a nearby one. In a clear vacuum, brightness falls according to a predictable geometric relation, but dust adds another source of dimming. Astronomers must separate distance from obscuration. A star can be faint because it is far away. It can be faint because dust blocks part of its light. It can be faint because it is intrinsically dim. Often all three effects are present. Careful measurement turns these possibilities into estimates. A pattern of spectral lines can indicate the type and temperature of the star. Its expected luminosity can then be compared with the observed brightness. The color change can suggest how much dust lies along the path. Parallax, when measurable, provides a geometric distance. Each method gives another constraint. This is how astronomy works with light that has been altered before arrival. The changes are not merely contamination to remove. They are also evidence about everything between the source and the observer. A missing wavelength can identify an atom. A reddened spectrum can reveal dust. A polarized signal can trace a magnetic field. A shifted line can measure motion. A dimmed star can help map a cloud. The photon's path becomes useful because it was not perfectly empty. There are places where this transformation has been observed across human time. When a star suddenly brightens behind dust, or when a moving cloud crosses a line of sight, telescopes can record the changing extinction. In young stellar systems, clumps of orbiting material may periodically block light from the central star. The repeating pattern offers clues about disks, warps, and developing planets. In other cases, the interstellar medium changes too slowly for one lifetime to notice. Its structures unfold over thousands or millions of years. Astronomers compare different regions and different stages using many separate objects to assemble a broader sequence. Light gathered tonight joins observations made by people who are no longer alive and will remain available for observers not yet born. A spectrum taken decades ago can be compared with a spectrum taken now. A photographic plate can preserve the brightness of a star before modern electronic detectors existed. The journey of the photon ends at the detector, but the record of its arrival can continue across generations. That continuity has changed the night sky from a collection of fixed points into a history of moving matter. Ancient observers used repeated star positions to navigate and mark seasons. Modern observatories still depend on repetition, but the measurements are far more precise. A star that once served as a stable direction can now reveal a motion of only a few meters per second through small shifts in its spectrum. The human relationship with starlight has widened without losing its original foundation. You still begin by receiving light. Everything else follows from learning how carefully to compare one arrival with another. Farther from Earth, the space between galaxies becomes thinner still. Dust grows less common, stars become widely separated, and photons may cross immense regions with few interactions. Yet even there, the universe is not a passive backdrop. Gravity shapes every path. As the journey continues beyond the local fields of stars and clouds, light begins to reveal not only the matter it crosses, but the geometry through which it moves. A photon crossing interstellar space may travel for centuries without touching a grain of dust or passing through a cloud dense enough to change it. Even then, its path is not independent of the matter around it. Gravity does not pull light in the way a hand pulls an object through air. A photon has no rest mass, but light moves through space-time, and space-time is shaped by mass and energy. When that geometry curves, the path of light curves with it. Near a star, the effect is small but measurable. Near a galaxy, it can reshape the image of another galaxy far behind it. Near a cluster containing hundreds or thousands of galaxies, the bending can stretch background light into long arcs, duplicate distant objects, or gather faint light into views that would otherwise remain beyond detection. The photon does not feel a force and decide to turn. It follows the straightest path available through curved space-time. This idea became one of the great tests of general relativity. During a total solar eclipse in 1919, astronomers photographed stars appearing close to the darkened sun. Their positions seemed slightly displaced because the starlight had passed through the sun's gravitational field before reaching Earth. The angle was tiny, yet it showed that the sun was not merely emitting light. Its mass was also shaping the route taken by light, arriving from much farther away. Every massive object does this. A planet bends light, a star bends it more, a galaxy bends it across larger regions. Usually the change is too slight to notice, but when source, lens, and observer align, gravity can become a natural lens. A distant, luminous object may lie behind a nearer massive one. Light that would have passed Earth can be bent inward from several directions, allowing more of it to reach the observer. The distant object appears brighter. Its apparent position may shift. If the alignment is close, but not perfect, the source may appear as several images around the lens. If the alignment is nearly exact and the mass is distributed symmetrically, the light can form a ring. This is called an Einstein ring. The ring is not a physical circle around the nearer galaxy. It is one distant source seen along many curved paths, arriving from directions spread around the foreground mass. Some paths are longer than others. Some pass through deeper regions of curved spacetime. Because of this, light from the same event can reach Earth at different times. A distant quasar may appear in several places around a lensing galaxy. Each image shows the same object, but not at the same moment. Brightness changes in the quasar can appear first in one image, then later in another. The delay may last days, months, or even years. By measuring it, astronomers can learn about the lens and the expansion of the universe. One source becomes several clocks, separated by the paths its photons followed. Gravity can also magnify light from stars too far away to study individually. When a foreground star passes close to the line of sight toward a more distant star, The nearest star's gravity can focus the background light. The distant star brightens for a time, then fades as the alignment changes. This is gravitational microlensing. The separate images are usually too close together to resolve, but the rise and fall in brightness can be measured. If the nearest star has a planet, the planet's gravity may add a smaller change to the lensing pattern. For a brief interval, a planetary system reveals itself, not by sending its own light, but by bending someone else's. Microlensing can find planets difficult for other methods and reveal faint or dark objects, including isolated stellar remnants. The lens does not need to shine. Its gravity is enough. A black hole moving alone through the galaxy may be almost invisible in ordinary light. But if it passes in front of a background star, the star's brightness and apparent position can change. The light exposes an object that emits little or nothing of its own. Absence of light does not mean absence of influence. A dark object can become known by the path it imposes on arriving photons. Large galaxy clusters create the strongest gravitational lenses commonly observed. Their visible galaxies contribute part of the mass, but the lensing pattern often shows that much more mass is present than the stars and hot gas alone can explain. The distorted background images help map that unseen component. Astronomers examine the direction and amount of stretching across many distant galaxies. From those small distortions, they reconstruct how mass is distributed through the cluster. The method is known as weak gravitational lensing, when the changes are subtle and statistical, rather than forming obvious arcs. Each background galaxy supplies a small clue. Its shape has been altered by the foreground structure. No single image may be decisive, because galaxies naturally come in many forms. But across thousands of examples, a coherent pattern appears. The photons arrive, carrying the imprint of matter they did not collide with. They may have passed far outside the visible edge of a foreground galaxy. Yet the geometry along their route has been changed by all the mass nearby, including material that cannot be seen directly. In this way, light traces the skeleton of the cosmos. The same bending that magnifies distant galaxies also limits what can be inferred from a simple picture. A bright arc is not the source as it would appear without the lens. Its shape has been stretched and folded. Astronomers build models of the foreground mass, then work backward to reconstruct the unlensed object. After correction, a galaxy that looked like a curved ribbon may become a compact system with regions of star formation. The lens has distorted the image, but it has also enlarged it. Without that foreground mass, the galaxy might be too faint or too small to examine. Gravity has acted as an imperfect telescope built from galaxies and dark matter. No mirror was polished, no glass was shaped. The lens formed because matter curved space-time long before anyone existed to observe the result. These alignments continue to change. A foreground galaxy moves. A background source varies. Earth orbits the Sun, while the Sun crosses the Milky Way. The geometry is never fixed, though much of it changes too slowly to notice without years of observation. In some microlensing events, the alignment lasts only days or weeks. In cluster lensing, the great arcs may appear stable across a human lifetime. The underlying motion is still present, spread across distances that turn movement into patience. Light keeps track of that geometry. Its direction on arrival reveals where the path ends, not necessarily where it began in a simple straight line. To locate the source, astronomers must understand the matter that stood between. This becomes even more important near black holes. A black hole is surrounded by a region from which light cannot escape once it crosses the event horizon. Outside that boundary, photons may still orbit, bend, or escape, depending on their direction and distance. There is a region near a black hole where light can follow circular paths for a time. These paths are unstable. A slight change sends the photon inward or outward, Light from glowing gas may curve around the black hole before reaching an observer. Photons from the far side of the accretion flow can be bent into view. The black hole's shadow is not a simple silhouette of the event horizon. It is shaped by captured and deflected light. The dark center is bordered by light that has taken extreme routes. Some photons reach the observer after circling partway around the black hole. Others may loop more than once, though each additional path is harder to detect. The image contains several versions of nearby material compressed and bent by gravity. Here, the journey approaches its limit. A photon aimed too far inward does not return. It crosses the horizon and can no longer send information to the outside universe. Another photon, differing by only a small change in direction, escapes. It may travel across millions of light years and end in a detector on Earth. The difference between capture and arrival can be set near the edge of a black hole, then preserved across the rest of the cosmos. Yet most photons never pass through such severe curvature. Their routes are shaped more lightly by stars, galaxies, and large-scale structure. Over enormous distances, even small effects accumulate into patterns that can be measured. There is also a weaker influence from the expanding universe itself. Between nearby objects held together by gravity, expansion does not pull systems apart in the way a stretching surface might suggest, but across distances between remote galaxies, space-time changes while light is in transit. The photon's path is not only passing through space, it is passing through a universe whose scale evolves during the journey. As the distance between large regions grows, the wavelength of traveling light grows with it. The photon arrives with less energy than it had when emitted. Its spectrum is shifted toward longer wavelengths. This cosmological redshift is not caused by dust, and it is not simply the ordinary Doppler effect of an object moving through fixed space. It reflects the changing scale of the universe between emission and observation. A photon that began as visible light may arrive in the infrared after crossing billions of light years. Radiation that once carried much higher energy can be stretched into microwaves. The journey changes not only direction, but scale. And as the photon continues outward from the first galaxies and earliest stars, the expanding universe becomes the next great influence on what finally reaches us. Beyond the gravitational fields of individual stars and galaxies, the photon enters a journey measured not only through space, but through the changing scale of the universe itself. Across nearby distances, cosmic expansion is almost impossible to notice. The Sun, Earth, and planets remain bound together. Stars remain held inside the Milky Way. Galaxies gathered into small groups can remain connected by gravity. On these scales, local forces preserve familiar structures. But between remote galaxies, the average distance grows with time. A photon traveling across that widening interval does not move more slowly. Every local observer still measures light moving at the same speed. What changes is the wavelength carried along the path. As the universe expands, the intervals between successive crests of the light wave expand with it. The wavelength becomes longer, its frequency becomes lower. Because a photon's energy is tied to its frequency, it arrives with less energy than it had when emitted. This is cosmological redshift. The name can be misleading because the shift may carry light far beyond red. Ultraviolet radiation emitted by a distant galaxy can arrive as visible light. Visible photons can arrive in the infrared. The amount of stretching is written into the spectrum. Atoms in a distant galaxy produce the same recognizable patterns of emission and absorption that they produce nearby. Hydrogen still leaves hydrogen's signature. Oxygen still leaves its own, but the entire pattern may appear displaced toward longer wavelengths. By comparing the observed pattern with wavelengths measured in laboratories, astronomers calculate how much the light has been stretched. This does not provide a simple distance in every case. The relationship depends on the history of cosmic expansion and on the motion of the source within its local environment. Yet for remote galaxies, redshift becomes one of the main ways of placing light within the history of the universe. The farther the photon has traveled, the earlier the scene it usually reveals. A galaxy seen 1 billion light-years away is not simply 1 billion light-years distant in an everyday static sense. Space has changed while the photon was in transit. The galaxy may now be much farther away than the distance the light crossed. At any one moment, there is the time the light has traveled. There is the distance to the galaxy when the light was emitted. There is the distance that separates us from the galaxy now. Cosmology keeps these ideas distinct because an expanding universe does not fit neatly into the picture of objects moving across an unmoving stage. The stage is part of the story. For the photon, none of this requires awareness. It moves locally through each region of space-time, according to the same physical laws. But when its entire route is considered, the changing geometry becomes visible in the wavelength that finally reaches a detector. A photon emitted when the universe was much younger can arrive after spending most of cosmic history in transit. During that time, stars were born and died. Galaxies merged, heavy elements accumulated, planets formed around later generations of stars. On Earth, oceans gathered, continents changed, and life took forms that did not exist when the journey began. The photon passed through all of this without waiting for any destination to become ready. Its arrival happens only because the path and the observer eventually meet. There is a present moment strangeness in that meeting. A detector cooled inside an observatory, a mirror turning with the sky, or an eye beneath a clear night can receive light that began before Earth carried complex life. The receiver belongs to now, the signal belongs to another age. Both are joined in one interaction. This is why astronomy can observe history without preserving it in stone or ice. The record is still moving. It continues across space until matter absorbs it. A fossil remains where it formed. Ancient light keeps traveling. The oldest photons that can move freely through the universe began their uninterrupted journey long before the first stars existed. Earlier than that, the cosmos was filled with hot plasma. Electrons moved freely among atomic nuclei, and photons scattered constantly from charged particles. The universe was not dark, it was opaque. Radiation filled every region, but it could not travel far in one direction before another interaction changed its course. In that respect, the early cosmos resembled the dense interior of a star, though the scale and evolution were different. As expansion continued, the plasma cooled. Eventually, electrons could remain bound to nuclei, forming neutral atoms. With far fewer free electrons available to scatter radiation, photons began to travel across large distances without interruption. The universe became transparent. Those photons still exist. Cosmic expansion has stretched their wavelengths into the microwave range, cooling the radiation to only a few degrees above absolute zero. They arrive from every direction, forming the cosmic microwave background. For this journey, the important point is the length of their passage. They have crossed almost the entire observable history of the transparent universe. Their route began before stars, planets, or mature galaxies. Small variations in the early distribution of matter were present, and over immense spans of time, gravity amplified them into the structures that later filled the cosmos. Photons continued onward while that transformation unfolded. Some passed through regions that would become galaxy clusters. Some crossed expanding voids. Some encountered changing gravitational wells that altered their energy slightly. By the time modern instruments received them, their distribution carried traces of the early universe and of structures encountered later. Even a photon that travels without colliding can have its energy changed by evolving gravity and cosmic expansion. The universe leaves marks through geometry as well as matter. Light from the first generations of stars began later. These stars formed from gas containing almost none of the heavier elements produced by stellar fusion. Their radiation helped change the gas between galaxies, stripping electrons from neutral hydrogen and gradually making intergalactic space transparent to ultraviolet light once again. This period is called reionization. It did not happen everywhere at once. Ionized regions grew around early sources and expanded until much of the gas between galaxies had changed state. Photons moving through that era encountered a universe whose transparency depended on wavelength and location. Some were absorbed by neutral hydrogen, others crossed ionized regions and continued toward the future. The surviving light is faint and strongly redshifted today. Observing it requires large mirrors, sensitive infrared detectors, careful calibration, and long exposures. Even then, astronomers may receive only a modest collection of photons from a galaxy containing billions of stars. The age of the source does not make the signal grand at the detector. It can end as a handful of electrical charges spread across a sensor. Yet those arrivals can reveal that stars were already forming. Galaxies were gathering matter and heavy elements were beginning to appear. A small signal can contain a large piece of cosmic history. Its origin is understood. Redshift also changes the apparent pace of distant events. If a source varies over time, cosmic expansion stretches not only the wavelength of its light, but the interval between arriving signals. A sequence that unfolded rapidly at the source can appear slowed to the observer. This is cosmological time dilation. A distant stellar explosion may brighten and fade over a longer observed interval than a similar nearby event. The effect provides another sign that expansion acts on the whole pattern carried by the light. Wavelengths are stretched, arrival intervals are stretched. The history arrives extended. There are limits to how far this journey can reveal. Because the universe has a finite age and light has a finite speed, we can observe only regions whose signals have had time to reach us. This defines the observable universe, though its boundary is not a wall in space. Beyond the farthest light we can receive today may lie more universe, perhaps extending far beyond what is visible. But no present observation can bring information from regions outside our causal reach, even within the observable universe. Expansion horizons are so distant, and the space between us is growing in such a way that light they emit now may never reach Earth. We can still see their earlier light, released when conditions allowed the path to close the distance. Their present becomes inaccessible even while their past remains in view. The sky can therefore contain images of places whose future signals will never arrive. This is not because their photons stop moving at light speed. They continue locally through every region they cross. But the intervening space grows in a way that prevents them from reaching us. A journey can remain possible at every local step and still fail to complete across the universe as a whole. For photons already arriving, the opposite has occurred. Their route remained open long enough. They crossed expanding intervals, curved regions, clouds of gas, and long stretches with almost no matter. Their wavelengths changed. Their directions may have bent. Their energy may have been absorbed and released again before the final leg. Then, after billions of years, the path narrowed toward one galaxy, one planetary system, one moving world. The universe continued to expand around them. Earth turned into the night. A telescope followed the source across the sky, and the ancient signal approached the small surface built to receive it. By the time ancient light reaches an observatory, most of its journey is over. What remains may be only a few meters through a telescope, a reflection from one mirror to another, and a final descent into a detector kept colder than the air outside. Yet, this last portion can determine whether the signal becomes knowledge or disappears into noise. A telescope does not merely make distant things look larger. Its first task is to collect. The wider the mirror, the larger the area of skylight it can intercept. Photons that would have fallen separately across a mountaintop or past Earth entirely are redirected toward the same instrument. Over time, the detector gathers their arrivals into a measurable pattern. For faint sources, patience becomes part of the instrument. An exposure may remain open for minutes or hours. Several exposures may be taken on different nights and combined later. The telescope follows the turning sky, while motors compensate for Earth's rotation, holding a distant galaxy or star on nearly the same part of the detector. The arriving photons do not form a complete image all at once, they accumulate. One interacts with the detector, then another. A faint region may contribute only a small number during an exposure, while a bright foreground star sends enough to overwhelm nearby pixels. Astronomers design observations around this imbalance. They select filters, exposure times, detector settings, and pointing strategies before the first useful photon is recorded. The universe provides the light, but the instrument determines which part of that light can be measured clearly. A filter may admit only a narrow range of wavelengths. A spectrograph may spread the incoming beam so that each wavelength lands in a different place. A coronagraph may block the direct glare of a star to reveal faint material nearby. Every device changes the route in a controlled way. Mirrors reflect, gratings separate wavelengths, masks remove bright regions, detectors absorb what remains. For infrared astronomy, even the telescope's own warmth can become a source of confusion. Objects at ordinary temperatures emit infrared radiation. The instrument may glow more brightly than the distant source it is meant to study. Cooling reduces that glow. Some observatories operate behind shields that block sunlight and heat from Earth or the spacecraft itself. Detectors may be chilled far below freezing. The quieter the instrument becomes in its chosen wavelength range, the more clearly it can register faint arrivals from space. Visible astronomy has other complications. Airglow, scattered moonlight, city light, and dust within the solar system can brighten the background. The raw frame is therefore a mixture. It contains the source, the background, and the instrument. Calibration begins the work of separating them. Astronomers measure how the detector responds when no light is supposed to enter. They identify pixels that behave differently from their neighbors, remove repeating electronic patterns, and compare several exposures so that random disturbances can be reduced. The goal is not to make the image prettier. It is to determine which part of the signal came from the sky. After calibration, the data may still look sparse. A distant galaxy can appear as a faint blur. A spectrum may contain only a weak line rising above the background. A possible planet may reveal itself through a tiny, repeated dip in starlight. Meaning often begins where the human eye would see almost nothing. Computers help organize these measurements, but they do not replace judgment. An apparent signal may come from a detector artifact, atmospheric variability, or an error in how the background was estimated. A pattern becomes trustworthy only after it survives comparison. Other nights are checked, other instruments are consulted. Independent teams may analyze the same target with different methods. The photon's arrival is physical. The conclusion drawn from it must still be tested. Near the edge of detection, a small calibration error can create or erase a line, and a background source can imitate the effect being sought. A claim may begin with a small excess of light in one wavelength. It may later become a map of gas around a star or evidence of a distant atmosphere. But between the first hint and the final conclusion lies repeated observation. The signal must remain. There is a generational quality to this work. A glass plate exposed in the 19th century can be scanned with modern equipment. A spectrum recorded decades ago can be compared with one taken tonight. A space telescope may observe the same field first photographed by an instrument that no longer exists. The observers change, but the light from the target continues to arrive. Each generation builds a different receiver. Early telescopes gathered visible light for the eye. Photographic emulsions preserved images beyond the instant of observation. Electronic detectors increased sensitivity and allowed measurements to be stored as numbers. Space observatories opened wavelengths that the atmosphere blocks. Now several instruments can observe the same object across radio, infrared, visible, ultraviolet, X-ray, and gamma-ray light, creating a layered account of different physical processes. Cool dust may dominate in the infrared. Young hot stars may stand out in ultraviolet. Gas heated to millions of degrees may appear in X-rays. Radio emission may trace cold hydrogen, magnetic fields, or fast-moving particles. These are not separate universes. They are separate ways the same universe releases energy. To combine them, astronomers align positions and choose how to represent wavelengths that human vision cannot see. An infrared band may be assigned red. An X-ray band may be shown in blue. The color is then a code, not a claim that the object would look that way to an eye. The translation is useful when its rules are clear. It can reveal structures that overlap in space but come from different temperatures or materials. A star-forming region may combine obscuring dust, newborn stars, and ionized gas. Each photon belongs to one part of that physical story. The final image is an arrangement of many journeys. Some photons began in atomic transitions. Some were released by warm dust. Some were produced when fast particles changed direction in magnetic fields. Some last interacted with matter long before Earth existed. At the detector, their histories become comparable because they arrive as measurable energy. Arrival time matters as well. Astronomers can record not only where a photon lands and how much energy it carries, but when it arrives. For changing sources, timing reveals structures too small or distant to image directly. A pulsar sends repeating beams across space as a neutron star rotates. A flare rises and fades. A planet crossing its star produces a regular decrease in light. The clock beside the detector becomes another kind of lens. A variation lasting minutes can place limits on the size of the region that produced it, because no coordinated change can travel faster than light. Repetition can reveal rotation or orbit. Delays between wavelengths can show that different parts of a system respond at different times. A photon's journey is therefore measured not only by distance, but by sequence. First one arrives, then another. The interval between them can carry information that neither photon contains alone. In large surveys, this process is repeated across wide areas of sky. Telescopes return to the same fields, building records of change. Objects that brighten, fade, move, or appear unexpectedly can be identified by comparing one observation with another. The sky becomes less like a fixed ceiling and more like a record of ongoing events. Yet, even the fastest event reaches us only after its travel time has passed. A star can explode in a distant galaxy, and its light may not arrive for millions of years. When it finally does, the event is already over at the source. The telescope receives the past in real time. The observation is happening now. The cause may belong to another era. For a listener resting beneath the present sky, there is no need to hold all those eras at once. The light does that on its own. It carries the delay without effort. It crosses the distance without requiring the observer to follow. By the time the signal reaches a mirror, nearly every part of the journey has already been decided by stars, matter, gravity, and expansion. The observatory contributes one final act of care. It turns toward the source. It gathers what arrives, and it preserves enough of the pattern for the universe to become readable. Every journey of light ends in an interaction. A photon may cross the atmosphere and disappear into a leaf, where its energy helps drive a chemical process. It may strike stone and become heat. It may enter the ocean, scatter through water, and be absorbed beneath the surface. It may reach a detector, free an electron, and become one measured point inside a larger record. There is no final resting place for the photon as an object. Its energy continues in another form. The detector may warm by an amount too small to notice. An electrical charge may move through a circuit. A number may be stored in memory and later displayed as part of an image. The original light is gone, but the result of its arrival remains. This is how much of astronomy is built. Not from photons preserved intact, but from transformations they caused. A spectrum on a screen is from the star that produced it by distance, time, mirrors, electronics, software, and interpretation. Yet the connection is physical. The pattern exists because light traveled from matter there and changed matter here. No telescope reaches backward to touch the source. The source reaches the telescope through radiation. For nearby objects, that exchange can feel almost immediate. Sunlight arrives within minutes. Reflected light from the moon takes only a little more than a second to cross the final distance to Earth. For remote galaxies, the same process becomes a bridge across cosmic history. A photon may begin when the universe contains younger galaxies and fewer heavy elements. It may travel while generations of stars enrich interstellar space, while planets assemble around later suns, and while life on one small world develops the ability to build a detector. The photon does not carry the events that occurred around it during the crossing. It carries the conditions of its emission and the changes imposed along its route. Its wavelength may reveal expansion. Its direction may reveal curvature. Its polarization may reveal magnetic structure. Its arrival time may reveal motion or scale. Its absence from part of a spectrum may reveal matter that absorbed photons like it. What is missing can be as useful as what arrives. A dark line in a stellar spectrum records an interaction that prevented certain photons from reaching the observer. A shadow across a glowing cloud records dust standing in the way. A dip in a star's brightness may record a planet crossing the line of sight. Astronomy reads both presence and interruption. The universe is not transparent at every wavelength, and no observer receives every signal. Some photons are absorbed close to their source. Some are scattered away from Earth. Some fall beyond the sensitivity of any instrument now operating. Others are still in transit. Light released from distant regions has not yet reached us. Light leaving Earth now begins its own outward passage, carrying traces of the sun, city illumination, radio transmissions, and the reflected brightness of the planet. Most of it will weaken into the larger background of space. A small part may cross another planetary system far in the future. It may pass through dust, bend near a star, or continue between galaxies without ever meeting a receiver. There is no cosmic requirement that light be observed. Observation is one possible ending among countless others. This places a natural limit on what can be known through light. Astronomers can study only what reaches a detector, and only through interactions that preserve useful information. Some regions remain hidden behind thick matter. Some processes emit radiation that cannot escape. Beyond an event horizon, no later photon returns to describe what happened inside. Beyond cosmic horizons, new signals may never cross the expanding distance. The observable universe is shaped by these limits. It is not the whole of existence. It is the portion from which information has had time and opportunity to arrive. Even within that portion, every image is incomplete. A visible photograph may emit cold gas. A radio map may miss hot plasma. An X-ray observation may reveal violent heating. while saying little about cooler stars nearby. Each instrument receives a selected range of the total radiation. Understanding grows by placing partial views together. The result is not a single perfect picture, but it's a set of measurements that agree well enough to describe a physical world beyond the observer. This agreement is one of the quiet strengths of science. A star's temperature can be estimated from its spectrum. Its distance can be measured through parallax or other methods. Its motion can be found through wavelength shifts. Its size can be constrained through brightness, models, and sometimes direct measurement. Different paths of evidence meet. When they do not meet, the disagreement becomes useful. It may reveal an error, an incomplete model, or a new condition that had not been considered. Light does not explain itself. It allows questions to be tested. Across centuries, those questions have moved from the visible arrangement of the sky to the physical nature of stars, galaxies, planets, and the universe itself. The same points once used to measure seasons now reveal nuclear fusion, chemical composition, gravitational motion, and cosmic expansion. The night sky did not need to change for this to happen. The receivers changed, the methods changed, the precision changed. What once entered the eye and became a familiar pattern could later enter a spectrograph and become a measurement of hydrogen. It could enter a camera and reveal a galaxy. It could enter a cooled infrared detector and show stars hidden behind dust. The photon's journey remained governed by the same laws. The meaning drawn from its arrival became deeper. There is no final instrument that will receive every possible signal. New telescopes extend sensitivity, resolution, and wavelength coverage, but each brings its own boundaries. Future observatories may detect fainter galaxies, map planetary atmospheres more clearly, or measure subtle changes in the light from distant worlds. They may collect photons that are already traveling now, crossing regions no one can monitor directly. Those future arrivals have already begun. Some left their sources before the instruments that will detect them were imagined. Their paths are approaching a technology that does not yet exist. In that sense, astronomy is prepared by the universe in advance. The signal starts first, the receiver comes later. A mirror may be built beneath light that has been traveling toward it for billions of years. Once the observation is complete, the data may continue long after the detector is replaced. Stored measurements can be re-examined with methods developed decades later. A faint pattern once dismissed as noise may become meaningful when compared with new observations. The physical journey of the photon ends only once. The informational journey can begin again each time the record is read. Still, every conclusion remains connected to that first event. Energy meeting matter. A photon enters silicon. An electron moves. A measurement becomes possible. Behind that small change lies a star, a cloud, a galaxy, or an earlier state of the universe. Between them lies the full route: emission, scattering, absorption, curvature, expansion, atmosphere, mirror, and detector. The path can be unimaginably long. The ending can be almost weightless. No sound announces the arrival. No visible mark appears on the instrument. The detector records one event among many, and the telescope continues following the sky. Another photon arrives, then another. Gradually, a point becomes a spectrum. A spectrum becomes a temperature. A repeating signal becomes an orbit. A stretched wavelength becomes a measure of cosmic history. The universe becomes readable one absorption at a time. And after every measured journey, the light is gone, while the pattern remains.